When you revolve a region in the plane about a line, it results in a solid, which is called a solid of revolution. The line that you're revolving around is called the axis of revolution. If we take a general function, y equal f of x, this line right here, and we revolve the region between f of x and the axis around the x-axis, we get a shape that looks like this. Now, in the disk method, what we do is we draw little disks, and they can change in width from a little width to including a lot of width between our base and the rest of our disk. Now, the area for each of these disks, or for each of these circles, is pi times the radius squared, which is your general formula for area, but the radius is the distance from your x-axis up to your function. Well, that's the value of the function at whatever value of x we are. So what we do is we make a disk, and the disk, this disk right here, we're going to move it over and make it a smaller disk, has width of whatever the change in x is from this circle to this circle. So when we do our volume, we're going to cut this into multiple disks. We're going to have a disk here, and then we'll have a disk next to that, and then another disk, and the more disks we cut it into, the more accurate our volume will be. As I explained with the demonstration that I used, the area of each, or the volume of each disk, is equal to pi times the value of my f of x function squared times delta x. To get the volume of the entire solid, we have to do a sum of each of these. Now from this point forward, we're going to call f of x r sub x, because, or r of x, because it's the radius. So this is the volume of each disk, but the volume of the whole solid is the sum for all of these disks from I equal 1 to n, the number of disks, of pi times each disk radius squared times the delta x of that radius. So that would be delta x sub I. Now, we did account for r sub x. This is the region, or the radius, if we have no core that's out. We'll have to create a different formula if we use two different functions for an area between. This is for one function and the area between that function and the x-axis. Okay, as we make the width smaller and smaller, which means we increase the number of disks, we end up with this. We end up with the limit as our delta x goes to 0, meaning our disks are thinner and thinner, of pi times sum from I equal 1 to n of r sub of x sub I squared times delta x sub I. Well, we know from the definition of an integral that this can also be written, I should put an equals there, as pi, because pi is a constant, we can pull it outside of the integral, of the integral from a to b of r of x squared dx, because dx is our delta x. For the first example, we're going to find the volume of the solid revolved around the x-axis that is created by the bounds y equals 4 minus x squared, which is this parabola, and the x-axis, and we're going to find it for the interval from 0 to 2. So my formula says that the volume equals pi times the integral from a to b of my r sub x squared dx. So in this situation, our volume equals pi times the integral from 0 to 2 of 4 minus x squared quantity squared dx. Now we need to multiply out the stuff in the parentheses. So we end up with the integral of 16 minus 8x squared plus x to the fourth dx. This is 16x when I integrate minus, we end up being x to the third, so that 8 has to be divided by 3, and then plus 1/5 x to the fifth, and again we're evaluating from 0 to 2. So now we evaluate. The nice thing is everything in this expression has an x in it, so we're only going to have to evaluate it 2. So we get pi times 16 times 2 minus 8/3 2 to the third plus 1/5 2 to the fifth. And we would end up subtracting 0, so we don't have to worry about that part. So what we end up with is 256 pi over 15. And in general, we don't change this to a mixed number because it doesn't make as much sense as a mixed number. Now I'd like you to try number 1 in the section exercises. Here is the graph that's given in the book. Pause the video, and then when you're finished, go back and watch the solution. Okay, so to solve this, we set up our integral. It is pi, almost forgot the pi times the integral from 0 to 1 of negative x plus 1 quantity squared dx. So the first thing we do is square out that negative x plus 1. And we get x squared minus 2x plus 1 dx. So now we have to integrate. The integration on this isn't too bad. Our pi is still out in front. We get 1/3 x cubed minus x squared, because the integral of 2x is x squared, plus x, and we have to evaluate from 0 to 1. As with the example, we don't have to worry about the 0 part, because when we evaluate at 1, it's going to give us an answer, but when we evaluate at 0, we'll get 0. So we end up with pi times 1/3 minus 1 plus 1. So the -1 and the +1 cancel, and we end up with the answer pi over 3.